A rare interstellar visitor, 3IATLAS, has just swept past Mars, and reports indicate that NASA's Mars Reconnaissance Orbiter targeted it with the HiRISE camera. Harvard astrophysicist Avi Loeb is urging NASA to release those frames now so the scientific community can examine the object's behavior from a unique vantage point. If the images exist at the expected quality, they could quickly resolve questions about its jets, dust, and possible fragmentation. The case for rapid release is not about headlines. It is about pixels that can settle debates. You already know the basics of 3IATLAS from earlier episodes, so let's move straight to why this moment matters. Hubble captured an image in late July that showed a teardrop-shaped dust coma and gave early constraints on size and activity. As the object moved inward, multiple teams planned observations around the Mars encounter and perihelion. Europe's ExoMars Trace Gas Orbiter and Mars Express watched in early October. China's Tianwen-1 released a Mars orbit detection from October 3rd that confirmed the target was within reach, even for instruments not designed for fast, faint interstellar comets. If those platforms could pull a detection, imagine what HiRISE might have recorded. HiRISE is famous for razor-sharp views of Mars, routinely mapping the surface at sub-meter scale when flying low over the planet. The resolution for a distant comet is of course far coarser, but even tens of kilometers per pixel can be decisive for morphology. Loeb has argued that HiRISE should beat the July Hubble view by about a factor of 3 in effective sampling. That step change could reveal the direction and spread of active jets, place limits on fragment separation, and distinguish a nearly symmetric coma from one skewed by outgassing on a rotating nucleus. Even if the signal is faint, a handful of well-timed frames can reveal structure that Earth-bound observers could not resolve at that geometry. Why does geometry matter so much? Because the object's appearance can be dramatically altered by viewing angle. Anti-tails that seem to point toward the Sun can appear when the observer crosses the comet's orbital plane, projecting a dust sheet forward. Narrow fans and corkscrew patterns can be produced by a small set of vents on a spinning nucleus. Without a second vantage point, those shapes are easy to misread. The Mars window gives us the triangulation we rarely get. Compare a Mars orbit view to Earth-based or Earth orbital images at similar times, and you can separate true physical structures from perspective tricks. So what is on the table already, and what is missing? Public data include the Hubble image from July, mission notes about the object's trajectory and safe December distance from Earth, ESA statements documenting Mars epoch observations, and the Tianwen-1 detection from early October. What has not appeared yet, as of the time of writing, are NASA's HiRISE frames from the Mars window. Some reporting linked the delay to administrative slowdowns around a government funding pause, which is a process story rather than a science story. The science story is straightforward. If HiRISE saw it, release the frames with the usual calibration notice and let the community work. What could those pixels settle, even if they look unimpressive to the eye? Start with jet geometry. A single limit on jet length or opening angle at the Mars phase angle feeds dust dynamics models that predict how tails should evolve after perihelion. Next, fragmentation. If any pieces are spaced by more than roughly a pixel at the HiRISE distance, that is a clean breakup signature. If the object remains a single unresolved head, that sets an upper limit on fragmentation for that epoch. Then coma asymmetry. Any measurable offset between the brightness centroid and the solar vector anchors models of torque and non-gravitational acceleration. Finally, crude color information. Even broadband differences, when cross-checked with ESA spectra and good ground-based photometry, hint at grain sizes and volatile layering. The default explanation to test first is also the simplest. 3IATLAS behaves like a comet. As solar heating increases, trapped ices sublimate and carry dust outward, creating a coma and tails. Study enough comets and you find that many so-called anomalies melt away once you correct for rotation, jet direction, and geometry. Anti-tails, sudden brightening, and odd orientations are not exotic by default. They are often the expected result of the dust environment and our changing viewpoint. Recent expert commentary after perihelion has emphasized that the object appears intact and does not show evidence of an explosion. That is the baseline to beat. The counter-arguments have gotten attention because they tap into genuine uncertainty. Some observers have pointed to reported tail orientations, brightness changes, or non-gravitational acceleration values that seem challenging for a simple sublimation model. Loeb's call folds here. He is not declaring a non-natural origin. He is demanding the best available data so those claims can be tested with real constraints rather than viral diagrams. Occam's razor says to keep the model as simple as possible until the data force you beyond it. A sharper Mars window dataset is the fastest way to learn whether we are looking at familiar comet physics or at something that does not fit. Transparency helps more than theory right now. Space agencies routinely release raw or calibrated frames with modest delay because the scientific value of many eyes outweighs the risk of misinterpretation. Releasing the HiRISE set would let independent teams measure the pixel scale, extract profiles along the tail axis, estimate upper limits on fragment separations, and compare the results with what ESA and Tianwen-1 saw around the same time. When different vantage points agree on a geometry-sensitive feature, confidence goes up quickly. When they disagree, we learn which interpretation leaned too hard on viewing angle. It is worth addressing a few persistent myths. The first is that a lack of immediate images implies something extraordinary is being hidden. In practice, administrative bottlenecks and processing queues explain most schedule slips. Meanwhile, other agencies have already posted detections, which argues against a coordinated blackout. The second myth is that sun-facing tails must be exotic. They are a known projection effect when the observer crosses the object's orbital plane. The third is that rumors of a mid-course explosion prove an artificial device. Current evidence does not support a catastrophic breakup. Extraordinary claims need extraordinary data, and that is exactly why the HiRISE set should come out. What would analysts actually do with the frames on day one? They would register the images, confirm the astrometric solution, and measure brightness profiles along several position angles. They would fit a model coma plus jet component to look for asymmetry. They would compare the jet axis with the solar direction to see if the offset matches expectations for outgassing. They would search for secondary peaks that might indicate fragments. They would compare the derived limits with simultaneous or near-simultaneous ESA and Tianwen-1 epochs to control for geometry. Even when the signal is faint, this workflow yields hard bounds that make or break specific claims. Consider the value of a null result. Suppose the frames show only a compact fuzzy head and a short, unresolved tail. That still caps jet length at the epoch and argues against large discrete fragments. It constrains rotation-driven asymmetry and limits non-gravitational acceleration that would arise from strong one-sided venting. Labs can fold those limits into thermal and dust models, and within days the chatter shifts from speculation to numbers. No spectacle is required for that to be a win. Now consider the value of a positive detection of structure. If the frames reveal distinct fans or stacked plumes, the opening angles and brightness ratios give clues to vent latitude and rotation rate. If there are two brightness peaks separated by more than a pixel, that is hard evidence of fragmentation. The separation, combined with timestamps, yields relative velocity, with even a rough mass estimate from light curves. That velocity feeds models of cohesive strength. Suddenly, we are not arguing about diagrams. We are talking about a measured event with uncertainties and implications. This is why Loeb's request resonates beyond any single hypothesis. Rapid data release is a transparency test for planetary science and a trust test for the public. The community has navigated similar moments before. When instruments caught unusual features on other comets, raw frames flowed to archives and the debate unfolded in the open. The same should apply here. The scientific risk of releasing a handful of faint Mars window frames is low. The potential payoff is clarity. What should you watch for next as a checklist? First, the HiRISE release itself. When it drops, look for a note on pixel scale, exposure time, and the observing geometry. Second, ESA quick looks from ExoMars or Mars Express that bracket the same dates. Those will help validate or challenge any jet orientations inferred from the NASA images. Third, ground-based follow-ups that track the anti-tail and any rotation-modulated features after perihelion. Fourth, comparisons with Tianwen-1's October 3rd detection. If a feature aligns across two platforms with different viewing angles, it is almost certainly real. The broader lesson is about how science turns uncertainty into progress. Interstellar visitors are rare. Each one is a chance to refine models of how small bodies form and evolve around other stars, and how they behave under our sun. When datasets from different platforms are released promptly and compared honestly, surprising claims either gain strength or fade away. Either outcome advances knowledge. If 3IATLAS turns out to be an ordinary comet behaving in a mostly ordinary way, that is still a valuable data point because it anchors the spectrum defined by Oumuamua and Borisov. If, after rigorous testing, something genuinely odd remains, the case will be built on measurements rather than on inference alone. So the request to NASA is simple and reasonable. Publish the HiRISE frames from the Mars window with the standard caveats about calibration and signal-to-noise. Let observers measure, model, and argue with data. The worst case is a blur that tightens the bounds. The best case is a set of features that decisively shape the next month of analysis as the object recedes. Either way, clarity beats speculation. And on what matters most. We have Hubble's July baseline, we have ESA's Mars Epoch observations, we have a release detection from Tianwen-1, add HiRISE from the Mars Reconnaissance Orbiter, and the community gains a rare four-corner dataset on an interstellar comet as it threaded the inner solar system. That is how planetary science should work. Open images, multiple angles, and models that rise or fall on the strength of the evidence.